Hello everyone, welcome back to another class of fundamentals of particle and fluid solid processing. Today, as I mentioned last time, that we will be doing some workout problem so that our concepts, theoretical concepts that we have seen, several expressions, how to utilize those, why those are necessary. I hope those things will be clear in this class. So, we start with a problem which says that 3.6 kg of solid particles of density 2590 kg per meter cube and surface volume mean size of 748 micron form a packed bed of height 0.475 meter in a circular vessel of diameter 0.0757 meter. Water of density 1000 kg per meter cube and viscosity 0.001 Pascal second is flowing upward through this bed. We have to calculate what is the bed pressure at incipient fluidization, the superficial liquid velocity at incipient fluidization, the mean bed voidage at superficial liquid velocity of 1 centimeter per second. We have to find out what is the bed height at this velocity, which means the superficial velocity of 1.0 centimeter per second, and pressure drop across the bed at this 1 centimeter per second of superficial liquid velocity. So, there are several questions here. The things that we have to calculate are bed pressure, superficial velocity at incipient fluidization, or say the minimum fluidization condition, and then we have to find out that what is the mean voidage when this velocity is at a certain value, that is here at 1 centimeter per second. At this velocity, quite naturally bed will be expanded, okay, because we have to check that at first that what is the minimum fluidization velocity. If this 1 centimeter per second is beyond that value, so definitely then the bed will be expanded. So, what is the bed height at this velocity and corresponding pressure drop when the liquid superficial velocity is at 1 centimeter per second. So, to sum up the information that are given, the bed weight when it is a fixed bed, that is mentioned. Then it is mentioned the particle density, particle surface volume mean diameter, the height it forms, the fluid that is flowing, that is water here, its density, viscosity, these information are given. So, if you at first draw a schematic, that if you have this is your packed bed, then what you have, this weight of the particles is known, or the mass, if I say, that is known. Then you have the particle density, which is the rho p. You have the value XSV, that is the surface volume mean diameter. We have the height, that is also known. It is of circular cross section. This cross sectional area, it is also known because the diameter of this vessel is given. The water is flowing upward. This water or rho fluid, it is mentioned, and mu of the fluid is also given. So, sufficient informations are provided First of all, we have to calculate what is the pressure drop at incipient fluidization, that is at the beginning of the fluidization or the onset of fluidization. So, how do we do that? For that, what we at first require is the bed voidage, and bed voidage we can easily calculate from this information, that the mass of the bed or the weight of the bed is given, and we know what is that, that is the solid fractions multiplied by the volume, okay, the overall bed volume multiplied by the particle density. That gives the weight of the particle, which is provided here, that is 3.6 kg. Rho p is mentioned. As I mentioned, the cross sectional area we can calculate because the diameter information is given, the vessel diameter. Height of the bed is mentioned. So, we can easily find out what is the bed voidage for the fixed bed condition. Now, at the incipient fluidization, what happens? This we have repeatedly mentioned, that this pressure drop, okay, is actually balanced by this way, that the weight of particles minus the upthrust on the particles, fine, is what, this is the force that is balanced by this frictional drag, which is the pressure drop here multiplied by the cross sectional area. So, weight of the particles minus the upthrust on the particle divided by the cross sectional area is basically the pressure drop at the incipient fluidization condition, because this is the balance it would have, and until the expansion point is reached, until the bed is fully expanded, this pressure drop will remain unchanged. This is the conditions that we have discussed in details during the fluidization theory. So, if we now focus on this expression and write those values, that is the weight of the particle and upthrust on the particle, which is basically the buoyancy force, okay, that is the volume of water that is being displaced by the volume of particles, okay. So, this mg actually initially had this rho f. To write that in the form of mg, we have multiplied that with the rho p and divided by that rho p. So, basically what we have here is mg minus mg multiplied by rho f multiplied by rho f divided by the rho p, divided by A is our del P. So, if we now replace these numerical values, that is, this becomes mg by A multiplied by 1 minus rho P by rho F by rho P, it gives a value of 4817 Pascal, because here the mass is known, G and A, all the values are given. The A comes from this value to the cross sectional area, because the diameter of the vessel is known. So, that means this is the pressure drop at the incipient fluidization, because this pressure drop will actually balance the weight of the particle, the apparent weight of the particle. The actual weight of the particle minus the upthrust that is acting on those particles by the fluidizing media. So, then by equating that expression we can find out, because on the right hand side all the informations are known. So, we can find out what is the del P. So, which means the first part, the bed pressure drop at the incipient fluidization, this is calculated. Now, the question is, what is the superficial liquid velocity at this incipient fluidization? How do we calculate that? There we can write this Argand equation, because now the pressure drop is known, okay, and this is the incipient fluidization, remember. So, the flow through packed bed, or because at this condition, at this incipient fluidization, it reaches the maximum voidage that is possible by the particle orientation. So, considering that fact that the Argand equation is still valid, in such scenario we can apply this Argand equation, both the parts, inertia and the viscous part. We can calculate, or we can find an expression that involves the unknown velocity term, because on the right hand side this del P we have just calculated for the incipient fluidization condition. Once we equate that, we get the U value which is required for the fluidization to start or to begin, which is the minimum fluidization velocity, which in this case it is 0.365 centimeter per second. So, first of all, to know the incipient fluidization pressure drop, we have equated the apparent weight of the particle with the pressure drop. Using that pressure drop, applying the Argand equation, we now find out what is the superficial velocity at that incipient fluidization condition. These are the first two parts of this problem. Then the question is, so here we can see that it is 0.365 centimeter per second. Now the question is the mean voidage at superficial liquid velocity at 1 centimeter per second, which means it is well beyond the minimum fluidization velocity. Minimum fluidization velocity was, or is that we have calculated, is 0.365 centimeter per second. Now the condition is that the bed is operating at 1 centimeter per second of fluidization superficial liquid velocity. So the question is, quite naturally, the bed voidage will change, the bed height will change, the pressure drop will change. So what is that? What are those parameters, or what are those values? Now when I say pressure drop across the bed changes, because this is the pressure drop that we basically measure, because frictional pressure drop, you remember, that would be unaltered during fluidization. Fine. So first of all, to know that what is the mean bed voidage at superficial liquid velocity at 1 centimeter per second, we can use this expression, the Richardson-Jacky expression, that this is the U and the UT for the single particle relation, that is the terminal velocity of single particle multiplied by the voidage to the power n. To calculate or to know the value of n, or to use the appropriate value of this index n, we have to know what is the Reynolds number range, or in which range this Reynolds number that is currently operating, it is falling. So now, if you remember the previous section where we discussed this CD REP square chart, because the point was here we have the information of the XSV or the particle mean diameter, but we do not know what is the terminal velocity. So, for that, for such case we applied CD REP square relation, or CD REP square is equals to constant, this condition on the standard drag curves, which created a slope of -2, and the intersection that we took as the Reynolds number. Okay. So, here similarly the Archimedes number we can calculate, because these are based on the particle and the fluid properties, and everything is mentioned, the required values. So, CD REP square, this value comes out to be 8704 in this case. So, if you use the same methodology or apply the same methodology to find out what is the intersection of this CD versus CD REP square constant, this line with the standard drag curve, we find that REP is 90. We see that this value appears to be 90, and accordingly we find out the terminal velocity of the particle as 0.12 meter per second, because all other parameters are known. And now, since this REP is 90, okay, in the last class we have seen that in such condition it is better to use the Kahn-Richardson's expression to find out the value of n. If we apply that, okay, and for this u of 0.01 meter per second, or which is 1 centimeter per second, we get the value as 0.46. So, that means at this velocity the voidage of the bed goes up to 0.46. So, from this expression what happens, that we get the value of n, because all the other information are known. Once we calculate n, we apply here having this ut known and u also known. Which gives us the value of epsilon, because ut here is this one, u is this one, and n we calculate from this expression. We apply these numerical values to find out what is epsilon from this expression, which is 0.46. So, which means our third question is also answered. Now, the question is, what is the bed height at this velocity? we use the simple relation. If you remember this expression as well, where we equated the volumetric flow rate between 2 points. The point 1, say it is the fixed bed condition, point 2 is the expanded condition, where the voidage is epsilon 2, and at fixed bed condition voidage is epsilon 1. In fixed bed condition H1 is known, we have to find out what is H2. We do that and we get the value of 0.572. So, this meter is the bed height when the superficial velocity is 1 centimeter per second. Now, the last part was that what would be the pressure drop at that superficial velocity. Now, the measured pressure drop, as I said, will include hydrostatic head of the liquid in the bed, okay, because the frictional pressure loss or the frictional head would be the same during the fluidization. So, if we apply the mechanical energy balance between point 1 and point 2, point 1 being the fixed bed condition, point 2 being the final state or the expanded state. Okay. Now, in both the cases U is same, but there is the height difference of this much initial to the final state. Okay, because the point is that there is the hydrostatic head in the liquid, and here the frictional loss is the pressure drop divided by the rho f g. So, what we get by replacing this expression here in this equation, we get the del P as 10,428 Pascal, which is the measured value. So, I hope this question is clear to you. Now, coming to the next problem. The problem says that a packed bed of solid particles of known density occupies a depth of 1 meter in a vessel of cross sectional area 0.04 meter square. The mass of solid in the bed is known, the surface volume mean diameter is given, liquid density and viscosity is also provided. So, we have to calculate the voidage of the bed, the pressure drop when the volumetric flow rate of the liquid is 0.72 meter cube per hour, and the pressure drop across the bed when it becomes fluidized. So, that means again similar to the previous problem, here the voidage calculation, okay, would involve the similar type of solution, that mass of the bed is given here, okay, surface volume, mean diameter, density, cross sectional area, everything is mentioned. So, we can find out what is the epsilon. Now, the second part, this involves the calculate pressure drop across the bed when the volumetric flow rate is this one. Okay. Now, assuming that the bed is not fluidized, we can apply Argand's equation to find out what is the pressure drop. If we do that, we find out the del P as 0.7876 Pascal, because all information here are known or given. Now the point is that whether this assumption is valid or not, we must cross check that. If we equate this pressure drop or find out what is the weight, apparent weight of this bed, okay, then what it happens, that it comes out to be with this voidage, the pressure drop would be 9839 Pascal. Okay. Now if we again look at this pressure drop for this particular flow rate, we see that this pressure drop is lower than this what would have been in the fluidized condition. So which means the bed will still not be fluidized at that 0.72 meter cube per hour of flow rate, because it has not reached that much of a pressure drop which can withstand the weight of the particle in suspended condition. So which means our assumption of using Argand equation that the bed is not fluidized, okay, this is valid, and the pressure drop at this fluidized condition would be this pressure drop. This is the answer for the third part. So I hope this becomes also clear to you, that how to determine the bed has fluidized or not based on the pressure drop calculation for a given flow rate. In the first problem what we did, we equated the apparent weight with the pressure drop to find out the value, that what happened, to find out the value of this U minimum fluidization, and we checked whether that minimum fluidization, the current operating velocity is over the fluidized that fluidizing UMF or not, the minimum fluidization velocity. If it is there, then we have used the expanded bed relations to find out what would be the bed height and the bed porosity. But in this case, we have compared the pressure drop to know that whether the bed has expanded or not. Okay, and in the third problem, we have 12 kg of spherical resin particles of known density, uniform diameter, water density, viscosity is given, vessel diameter is given, the formed packed bed height is also mentioned. So we have to calculate what is the pressure difference between the base and the top of the bed, and for a certain water flow rate, what would be the resultant bed height and bed voidage. So provided all the information are given, first of all we have to calculate what is the pressure difference between the base and top of the bed. So again, the pressure drop in the bed we can find out by such expression that we have done in the first problem, that the weight minus the upthrust divided by the cross sectional area. Here the cross sectional area is multiplied here itself, and here this is the expression. So we find out what is the frictional pressure drop. Now since this calculation will involve, as I mentioned, what is the difference, pressure drop difference between the base and top, that means since there is a water flow, it has its hydrostatic force as well, head loss. So which means now here we can apply the similar methodology, applying mechanical energy balance between point 1 and 2, where u1 is equals to u2, because the velocities are same at those 2 points. and there is a height difference of this much, we get the measured del P between 0.1 and 0.2 is 2730 Pascal. Now again we go for this Richardson-Jacky expression. We find out what is the superficial velocity, because the question is for this water flow rate. Okay, we know the bed cross section, so what is the superficial velocity, and at that condition whether what is the resultant bed height and bed voidage. So at first we find out from the given information what is the superficial velocity. Now here all expressions are given to calculate the terminal velocity. We calculate the terminal velocity. With that terminal velocity we find out the Reynolds number, and we see that the Reynolds number value is 0.03, which means we can use this relation to find out the value of N. In earlier case we used the Khan-Richardson expression, here we can use the Gelder's expression, which means this relation is valid for this particular Reynolds number because it is beyond 0.3. So we find out the bed voidage from this expression, because now here the u is this one, superficial velocity, the terminal velocity is this one, and n is known. So we find out what is epsilon. Once we know the epsilon, we know the mass of the bed, we can find out what is the height of the bed by this relation, which we are using almost all the workout problems, that gives the height as 0.465 meter. So to sum up this fluidization, here is the chart that will help you to remember possibly, is that these are the conditions in this fluidization, the point A or the case A, B, C, D, E, F. Now in A, few particles, once the gas flow starts, few particles will vibrate if those are in loose conditions or orientations, but the same height as of the packed bed is there. As you further increase the gas velocity, the drag force becomes equals to the apparent weight of the bed, but it increases the bed voidage. If you further increase the gas velocity, the onset of bubbling will take place. So this is the increasing gas velocity condition. If the bed is narrow, the slugging operation will take place with increasing gas velocity. This we have discussed as well. If you further increase in any kind of fluidized bed, there will be a vigorous motion of the solid particles, and instead of bubbles you would see the turbulent motion of the solid particles, the pockets of solid particles, clusters of solid particles, turbulent motions of those things, and the upper surface basically vanishes. I mean, there is no as such identified a particular clear surface that you can find out. And if you further increase the gas velocity, the particles will be entrained or going out with the flow. So these are the different fluidization regimes or operating states. The reason behind this we have discussed, we solved some problems, and with this I conclude this section, and I hope that it has been beneficial to you. So in the next class we will be seeing a next section, new section. Okay. Until then, thank you for your attention.